Okay, so if from my title you're probably all wondering what the hell is a knowledge infrastructure. My research group started developing this idea a few years ago, and many other people are also using it. It's not just us. The idea is that there's a lot of discussion about infrastructure now. We are primarily historians and sociologists of science and technology, so we look at a lot of technological systems, and we see that there are infrastructures that are much more than technological systems. They include people and institutions as well as equipment. So a knowledge infrastructure generates, shares, and maintains knowledge in a routine and widely accepted way, and we have a number of examples. There are many others. The best there are perhaps research universities, a system that goes back to the 1600s, and national census bureaus, also very old. The World Weather Watch and the IPCC. So let me talk just a little bit about the technological side of this, but of course it's also a story about people and institutions. Just in terms of the historical temperature record, only that, and there are many other sources of data in climate science, of course. Just in terms of that, this infrastructure developed to the point that by 1900, most of the northern hemisphere on land was pretty well covered by surface stations, and by 1960, almost the entire world's surface pretty well covered by surface stations. That data was sent around by telegraph, by shortwave radio, by many other techniques, and reached literally around the world, even in the 1920s and 1930s. Not all of it, and not in the same way it does today, but still much of it was processed like that. In weather forecasting, in the 1960s, the World Weather Watch program began, really just a kind of formalization of this older exchange system, but this graphic gives you some idea of just how complicated it is with sensors on land, at sea, in space, and computer systems at a number of world centers that receive data from all over the planet, process it, and then send it back out to national weather services, which do many kinds of things with them, as well as weather forecasting. An interesting thing about the World Weather Watch is that it was a digital infrastructure long before the internet and did not rely on the internet for the first 20 years or so. So now, let me talk a little bit more about knowledge infrastructures. We have some very old scientific traditions that are part of why our heritage of knowledge infrastructures work as well as they do. In science, one of the most important things, of course, is credibility. And from that you get authority and sometimes trust. In a distant world of maybe 15 years ago, reputation systems were based on your pedigree, who taught you, where you went to school, your past performance, your track record, and on peer review, what other people in your field think of your work. Expertise was seen as a kind of a pyramid in which people at the very top were well known, they were ranked, there was a clear sense of hierarchy, and there were institutions that embodied that hierarchy, such as National Academies of Science, the Nobel Prize, and many other similar things. Peer review, again in this distant world of 15 years ago, but going much further back, of course, was done by other experts in the same field as you. It took place not only in terms of formal journal peer review, but also in lots of informal modes. Discussion in the hallway, sending letters, talking to people at conferences, presenting early drafts, and so on. And then finally went through a formal process in which a journal reviews an article, 2 or 3 people help with that process, you get a revise and resubmit, and you send it back in until that cycle's over and it's published. And then that process is finished, and that result is then fixed because it is published. In that world of peer review, data and code could be reviewed, but they rarely were. In fact, instead, what happened was that publications presented simplified versions of methods, that is, the quick and dirty, the the essential elements of your method, and your analysis of the data, but not the raw data themselves. Data and computer models were properties of the creator. They were work products, and so they belonged to you. And what happened to most data in most sciences was that they simply sat in a drawer until you lost them. This was also true because data were very voluminous and expensive, therefore, to publish on paper. So it wasn't just simply mostly wasn't done. So that meant that publications and results traveled in the world, but raw data and computer code did not. So this is an example of various results. I mean, these go back to 1881. They are the processed, analyzed data, and this is the typical kind of outcome of a scientific process in this now somewhat distant world. In climate data, one of the things you see, it's quite interesting, so this is world weather records from 1927. Here are the monthly temperature averages for Zanzibar in East Africa. And what you see is that already these are not raw data. These have been processed by the people at the weather station who report this. They take mean, they add the daily maximum and the daily minimum, and they divide it by 2, and then they average it for the month. So that processing has already been done by the time these data are published. And one of the tasks of data people in climate science has been to go back and revisit all of those records over and over again, looking for ways in which they might be not quite right and ways that they can be fixed. In this earlier world, here's another phase, not paper publication, but punch cards. There were billions of punch cards at major meteorological centers by 1950. These are punch cards stored in the main entrance hall of the National Weather Center, Weather Records Center in Asheville, North Carolina in the 1950s, when they were actually seriously worried that the building might collapse under the weight of all these cards. So here's an example of publication in modeling. We have on the one hand the published GISS model description. This is, of course, very recent, and of course I know I'm going to get to the fact that we publish model codes now, but the model code is on the right, the published description is on the left. It gives the math. The model code also gives the math, but is, of course, much longer because it has to be converted into a series of operations. All right, now I'm going to talk about one little piece of this knowledge infrastructure about climate change, stages in the history of climate modeling. It started with a kind of craft phase in which one or two or a small group of people would get together and build a climate model, often a climate person with a programmer. For example, Yale Mintz, Akio Arakawa. Arakawa was a programmer. Yale Mintz never wrote a line of code in his life. They built an important climate model at UCLA. So we could call this phase the craft phase, in which everyone, there are a few groups doing it. They're more or less working independently. They don't share code. They might share math. Later, you get a phase in which this moves to a kind of lab level as it becomes the central tool for climate modelers. So their models are built by a lab with now a more developed hierarchy. There are professional programmers. There are now different kinds of expertise, such as ocean modeling, especially in the 1970s, and then later many other sciences also represented. Teams working on models grow larger to the size of, say, 10s or 20s. And at this point, computer models begin to be shared. In the book I wrote about climate models and climate data, I did a kind of family tree of climate modeling. It's very schematic. There's a lot of missing data and missing models and missing information here, but it gives you some idea of how a few modeling groups begin in the late 1950s and early 1960s, and those then move to other modeling units which develop them or recode them or start with them and then throw them away and build their own. The most recent phase, the one in which we're still in, is what I would call the community phase. I mean, the lab phase still exists. There are still labs that just work on their own models and don't really interact that much on the modeling level. But we also have community models, which are much larger, involve hundreds of people. often have a dedicated programming staff that does nothing but work on those models. There is a widely varying involvement of scientists with coding. So many scientists work on the code directly, but some work mostly with math. There is, and one of the most important points that's already been referenced by Spencer is that there are lots of coupled submodels that demand a wide range of kinds of expertise. Increasingly over time, more and more sciences have kind of been recruited into climate modeling because more and more processes have been recognized to be important. These are major models. Each bubble shows a piece of the model in a different color, and the bubble is proportionate to the size of the code in that model. And the little arrows going back and forth are pipelines that kind of connect the pieces of the model and couple them together. So the largest climate models are approaching 1 million lines of code at this point. This is from a couple of years ago. Some of them have grown even larger since then. And here's a kind of governance chart of the community Earth system model. And what you can see here, if you can read this, is we have an atmosphere model, land ice, land model, ocean model, polar climate, biogeochemistry, and so on. A software engineering group, standing alone, a social dimensions group, and each of these, they have a huge meeting every year with up to 300 people in attendance, and that's only the tip of the iceberg of the people who work on and with this model. The community is very distributed. Their leaders of some of these working groups are at Los Alamos, Argonne, Livermore, and so on. So it's a very different, much more modern, distributed kind of work process, and it's also a lot more complicated, which creates many governance issues and communication issues for the people who are trying to build these things. So complexity increases in Earth system modeling, which is this little box here. But of course, then for the climate change issue, we have to get even bigger and begin to think about other aspects of the physical environment, such as soil and forestry, and policy and human activity, agriculture, forestry, energy, the economy, and so on. And one of the phenomena you see across the sciences is that many sciences are integrating around models and trying to find ways to couple one model to another, not always with beneficial effects. This is from Brian Lawrence at the British Atmospheric Data Center, and this point he makes at the bottom is very important. This is not just a technical kind of problem. There are lots of language issues. People call the same thing by different names, and they use the same name for things that they understand somewhat differently. There are issues of institutions and organizations that I'll come back to in a minute. Okay, so where are we going? One of the things, I highly recommend this book. It's a popular book, but it's by a very smart guy, and the last chapter is about scientific infrastructures. This is his chart, his language here. All these kinds of things are happening to science, where everyone is aware of it. Bigger and bigger, more data, more models, more linking, less hierarchical and less centrally filtered, and that's the aspect I want to get to now. So one of the things that people, the sort of hype version of what's happening in the age of the web is that now everyone can participate in everything, and that people will. We see this in open source software and other kinds of open source cultures, Kickstarter and many other things, that crowds are actually interested in participating in all kinds of things you might never have guessed they would want to do. So perhaps, some people hope, we will get a culture of extreme openness where everything, data, models, thoughts, random ideas, will be kind of up there on the web, and that will be good. This idea of a cognitive surplus, we have lots of smart people in the world who maybe aren't experts in everything about climate, but know something about some little piece and could make a contribution even though they're not professionals. And there is a growing movement that calls itself reproducible computational science. This started in the machine learning community, but is spreading widely. There have been about 100 conferences on this theme in the last 10 years. The challenge of reproducible computational science is to make all results in science reproducible by someone else without going through you, so that they can be independently verified. So the idea is you publish your data and you publish the analysis model that was used with it, or, sorry, 3 minutes, oh boy. And then other people will be able to reproduce it. That actually gets very difficult because you need not only models and data, but also expertise. And especially in meteorology and climate, that is not nearly as widespread as expertise about code. I think I will pass over this in the interest of getting to the conclusions here. So we're seeing a number of phenomena. We see a certain amount of citizen science in climate science. Sometimes, as in the case of our friend Anthony Watts, not necessarily with the intent of improving the climate change projections, but of disproving them. That has, there's a project, surfacestations.org, a very interesting thing because the data collection that it did has actually been useful for scientists, but not perhaps because of what Watts was hoping. We see climate audits, and this is we have certain people in this room who know way too much about this, but these are the idea that climate scientists shouldn't be auditing their own work. We should have people who aren't climate scientists auditing it because climate scientists are self-interested. They have an investment in the idea of climate change. There's a notion that peer review is a mistake. That really what that is pal review, review by your friends. So we need review by entities that are not part of the mainstream science system. And everywhere in the world, not just in climate science, we see a phenomenon that public trust is requiring more and more openness, more transparency. This is a kind of ideology. It is not always the case that transparency is beneficial to organizations or work efforts, but it is increasingly demanded, and we're not going to get away from that. We see open peer review processes emerging in which journals will put up preprints and allow anyone to comment on them. We have had a lot of challenges to the IPCC process and structure, encouraging that agency to develop more transparency, and lots of new possibilities for opening up this black box of science. There have been some kind of bizarre effects of this. So there are preprint circulation, lots of things like that are old, but there's also an increasing trend towards self-published books, which escape entirely from the peer review process, fake journals that exist to make money, blogs being even more important than actual publication, and many of those things, most of them are not peer-reviewed at all. There's a trend toward open source climate models, and I have 2 more slides, so I'm predicting lots more participation. This is coming if it isn't here already. There will be review of everything by lots of people, lots of actors who aren't part of the traditional process. These trends may be beneficial and they may not. And the challenge is what to do about that. So my theory is Aikido, the way of harmony of energy. Blend with the energy of your attacker and turn it to some useful purpose. So you're not going to stop this process. You can't kind of turn it back to a narrow model of the pyramid of expertise. We have to find ways to integrate that desire for openness and use it for scientific advantage and for the advantage of communicating about this problem.